So today we're going to talk about resistance, the third important aspect of circuit work. First, we're going to define resistance, and then we're going to learn to calculate resistance from current and voltage. When electrons flow through a bulb or any other conductor, the conductor offers some obstruction to the current. Now, mathematically, we only ever consider a component as having resistance, but it's a good moment to point out that the conductors themselves, the wires themselves, offer some resistance to current flow. So all wires have natural resistance. What we do mathematically is we assume that that resistance is negligible. A light bulb, for instance, has a very, very thin filament, and that causes a massive obstruction to the flow of current. So what we say is that the resistance of filaments are high. Resistance of wires is very low in comparison. So even though there is some obstruction, compared to something like the filament in a bulb, it would be very, very small. Current passes through easily and little energy is lost. So if the obstruction is called electrical resistance, in mathematical work we only consider that resistance which is considerable. So the idea of resistance is a reflection of the effect that a component has on a circuit, the effect that it has on the charge as it flows through it, slowing it down, and also the effect of the energy transfer. As the electrons are affected and their flow is reduced, the amount of energy that's released, or transferred out of the circuit, is also affected. The resistance, by definition, of a component is defined as the ratio of potential difference to the current going through it. So you can work out the resistance of a component, the resistance of a light bulb, by dividing the potential difference across it by the current flowing through it. Resistance is a scalar, and it has units of ohms. These are derived units, and 1 ohm is then equal to 1 volt per ampere. Remembering that the volt is also a derived unit, you could also express that in terms of joules per coulomb, etc. But we won't do that here. Light bulbs aren't the only thing that have resistance. And in fact, they're as part of electrical engineer's job would be to design circuits and control the current through different types of very complex circuits. So it would be important to use little components like these ones, these are called resistors, to finely adjust the current and potential difference in different complex circuits. You're probably used to seeing circuit boards like these if you've ever taken anything apart. What you can see here are different resistors, loads of them. And in fact, the coloured bands here represent numbers. If you're an electrical engineer or you work with electronic circuits, you'd get used to this numerical system. You'd be able to calculate directly what the resistance of all these circuits are. But basically, resistances are an extremely important part of circuit design. So the question is, how would you manipulate the amount of resistance in a circuit by using all these different little components? Well, there are some rules for combining resistors in series and parallel. And on the one hand, there are two relationships, and then there are the derivation of those relationships. So I'm going to talk you through both of those things. I'll introduce the two relationships first. The relationship for putting resistors in series, like this, is as follows. The total resistance, RT, is equal to the resistance of the individual resistors. Okay, I'm not going to discuss the proof just yet. So RT is equal to R1 plus R2. So that would be the relationship for resistance in series. The resistance in parallel is a little bit more complex. Here we go. 1 over RT, 1 over the total resistance in parallel, would be equal to 1 over each individual resistance separately. So if I have a situation like this one where I have 3 resistors in parallel, then I can find the total by working out 1 over R1 plus 1 over R2 plus 1 over R3. That would give me a number which would be equal to 1 over RT. So the inverse of that total would give me RT. Let's try a really simple question. Here we have 3 resistors in parallel. Each of them are 20 ohms. I want you to use the relationship for resistors in parallel to work out the total resistance of these 3 together. Stop the video and see if you can do it. The relationship is 1 over the total resistance equals 1 over 20 plus 1 over 20 plus 1 over 20. Hopefully you can see that 3 times 1 over 20 is 0.15. So that means that 1 over the total resistance equals 0.15. So if you do 1 over 0.15, you'll get something approximately 6.7 rounding up, which is the total resistance, 6.7. Once we know that this part of the circuit is equal to 6.67, we can now find the total resistance due to all the resistors. This one is 6.7 plus 20 plus 20. Because in series, the resistance is added. So what we've got here is 20 plus 20 plus 6.7 is 46.7. And that's how to calculate resistance in series and in parallel. Try the questions associated with this section now, and then when you finish, go on to the next video.